There's something hauntingly beautiful about the way the universe keeps its secrets. Gaze up at the night sky, and you'll see countless stars, galaxies, and nebulae, each one a masterpiece of cosmic artistry. But hidden among these celestial wonders are patches of darkness so profound, they seem to swallow the light itself. These aren't empty voids. These are dark nebulae, mysterious clouds of dust and gas so dense, they block out the stars behind them, leaving behind silhouettes of pure cosmic mystery. And what's even more astonishing, some of these dark nebulae don't just hide the light, they defy everything we thought we knew about how the universe works. Imagine a place where the laws of physics seem to bend, where familiar rules don't quite apply. That's what astronomers are finding as they study these enigmatic structures. Some dark nebulae are so cold they challenge our understanding of temperature itself. Others harbor bizarre magnetic fields, twisting space in ways we can't yet explain. And then there are those that appear to be alive, not in the way you might think, but in the sense that they move, shift, and evolve in ways that suggest something unseen is at work. It's almost as if the universe is whispering secrets in a language we're only beginning to decipher. That's why today we're diving deep into 25 of the most baffling dark nebulae ever discovered, each one a riddle written in stardust and shadow. From the eerie Horsehead Nebula, a cosmic ghost frozen in time, to the in-sky depths of Barnard 68, where stars simply vanish without a trace, these are the places that keep scientists awake at night. What's hiding inside them? Why do some seem to defy gravity? And could they hold clues to the very origins of life itself? Stick around, because by the end of this journey, you'll never look at the night sky the same way again. The darkness isn't just empty space, it's a canvas for the universe's greatest mysteries. Barnard 68 is one of those cosmic oddities that looks like a mistake, a hole punched straight through the starry canvas of the night. Nestled in the constellation Ophiuchus, it's a perfect sphere of darkness so dense, not a single star shines through it. If you were to point a telescope at this patch of sky, you'd see nothing. Just an in-sky void, as if someone turned off the lights in that corner of the universe. But here's the thing, it's not empty. Barnard 68 is a stellar nursery, a cocoon of cold gas and dust so thick, it's actively collapsing under its own gravity, preparing to birth new stars. What's truly baffling, though, is its shape. Most dark nebulae are irregular, twisted by magnetic fields or stellar winds, but Barnard 68, it's unnervingly round like a cosmic marble. Astronomers can't fully explain why. Some theories suggest it's in an early, undisturbed stage of collapse before outside forces warp it. Others wonder if there's an unseen force, a magnetic cage or even dark matter, sculpting it into this perfect form. And then there's the way it swallows light. This nebula doesn't just block starlight, it absorbs it with dust particles so efficient, they extinguish nearly all radiation passing through. Infrared telescopes reveal its hidden structure, a frigid core, colder than the void of space itself, where temperatures plunge to just 10 degrees above absolute zero. It's a place where chemistry slows to a crawl and molecules huddle together in the dark, waiting for the spark of creation. Barnard 68 isn't just hiding stars. It's hiding secrets about how stars form, how matter behaves in extreme cold, and why some corners of the cosmos refuse to play by the rules we think we know. And as it slowly contracts, one day it'll ignite. But for now, it remains a silent, shadowy sphere, a reminder that sometimes the universe's most profound mysteries are the ones we can't even see. The Coalsack Nebula isn't just another dark patch in the cosmos, it's one of the few dark nebulae you can actually see with your naked eye. Drifting right beside the Southern Cross, this vast cloud of dust appears like a stain against the brilliance of the Milky Way, as if a giant hand smudged the starlight from the sky. Indigenous Australians knew it well long before telescopes existed, weaving it into their celestial stories as a dark emu in the night, a creator spirit watching over the land. But what makes the Coalsack truly fascinating isn't just its visibility, it's the way it defies expectations. Unlike most dark nebulae, which are dense and uniform, the Coalsack has strange, gaping holes in its structure. Some regions are so thin they let starlight trickle through, while others are thick enough to blot out entire sections of the Milky Way. Why? Astronomers aren't entirely sure. Turbulent stellar winds might be tearing through it, or hidden magnetic fields could be sculpting its shape. Some even speculate that ancient supernova punched tunnels through the dust, leaving behind these eerie voids. Then there's its role as a cosmic light blocker. The Coalsack doesn't just obscure stars, it filters them, dimming the Milky Way's glow in a way that reveals the delicate structure of our galaxy's spiral arms. Without it, the night sky near the Southern Cross would be a blinding sea of stars. Instead, it gives us a shadowy silhouette, a rare glimpse into how dust shapes our view of the universe. But perhaps the most haunting question is what's hidden inside. The Coalsack is cold, silent, and brimming with complex molecules, the building blocks of life. Could pockets of this darkness be cradling newborn stars, invisible to our eyes? Or does it hold something even stranger, something we haven't yet imagined? One thing's certain, this isn't just a hole in the sky. It's a doorway, and we're only beginning to peer through. Slithering through the constellation Ophiuchus like a celestial serpent frozen mid-strike, the Snake Nebula is one of the most striking examples of how chaos can create beauty in the cosmos. Unlike the smooth, cloud-like shapes of most dark nebulae, this structure stretches an astonishing 80 light-years in length, twisting and turning with filamentary precision. Its body isn't just dark, it's threaded with intricate knots and tendrils so dense they appear almost solid against the starry backdrop. But what really sets this cosmic serpent apart isn't just its appearance, it's the invisible forces wrestling within it. Magnetic fields here don't just guide the nebula's shape, they dominate it. Imagine cosmic forces like invisible hands stretching and contorting the dust into these eerily perfect coils. These fields are so strong, they prevent the nebula's gas from collapsing under gravity's pull, defying one of the most fundamental rules of star formation. Normally, when enough material gathers in one place, gravity wins and stars are born. But in the snake's knotted filaments, particles align along magnetic lines like iron filings, creating a bizarre cosmic tug of war where magnetism overpowers gravity itself. Some sections are so magnetically locked, they've remained stable for millions of years, stellar nurseries frozen in time. The contrast with typical nebulae couldn't be sharper. Where most star-forming regions billow like smoke or pool like liquid, the Snake Nebula's structure is all sharp edges and tension. Its darkest knots, dubbed magnetic cores by astronomers, glow faintly in submillimeter wavelengths, revealing temperatures just 15 degrees above absolute zero. These aren't just cold pockets, they're cosmic freezers, preserving molecules that would normally be torn apart in warmer environments. Some researchers believe these ultra-dense knots could be cradling an entirely new class of failed stars, objects too small to ignite, yet too massive to be planets. What makes this serpent so mesmerizing isn't just what we can observe, but what it implies. If magnetic fields can halt star formation on such vast scales, could other dark nebulae be hiding similar surprises? Are we seeing a rare cosmic battle, or just the first chapter of a story we're only beginning to read? The snake doesn't just coil through space, it winds through our understanding, pulling us deeper into the mystery of how darkness shapes the universe. Hovering near Orion's belt like a shadowy sentinel, LDN 1622 isn't just another dark nebula, it's a cosmic optical illusion. From our vantage point, this dense cloud appears to cling to the iconic trio of stars, almost as if it's part of their celestial display. But in reality, it's far closer to us, a mere 500 light-years away, making it one of the nearest dark nebulae to Earth. What seems like a simple blot of darkness is actually a stage for one of the universe's most deceptive performances, where light and shadow dance in ways we're still struggling to interpret. Peer into its depths with visible light telescopes, and LDN 1622 gives nothing away, just an impenetrable veil, but switch to infrared and the entire scene changes. Hidden behind that curtain of dust, newborn stars flicker to life, their heat glowing through the cold shroud like distant lanterns in fog. These protostars are so young, they haven't even begun nuclear fusion yet, cocooned in swirling disks of gas that might one day become planetary systems. The nebula's darkness, then, isn't just absence, it's a theater curtain hiding the earliest acts of stellar birth. Yet what's truly puzzling astronomers isn't just what's inside LDN 1622, but what makes it so dark in the first place. Some argue its opacity comes from sheer density, with dust particles packed so tightly they snuff out even nearby starlight. Others point to its peculiar composition, a mix of complex carbon-based molecules and silicate grains that might absorb light more efficiently than typical cosmic dust. There's even a wilder theory. Magnetic fields could be aligning these particles like microscopic blinds, controlling how much or how little light escapes. The debate touches on something deeper. If darkness isn't always about quantity but quality, not how much dust exists but what it's made of, then our entire understanding of these cosmic shadows might need rethinking. LDN 1622 challenges us to look beyond what's missing and ask why it's missing. Every photon it blocks, every star it hides, is a clue waiting to be decoded. And with Orion's belt glittering nearby, it's a reminder that sometimes the universe's brightest wonders are framed by its darkest mysteries. Stretching across the heart of the Milky Way like a discarded relic from some cosmic giant, the Pipe Nebula presents one of the most striking silhouettes in the night sky. This isn't just a random smudge of darkness, it's a carefully divided structure, split into two distinct sections so perfectly formed, they look almost intentional. The bowl sits heavy and round, while the long, slender stem extends gracefully, creating an illusion so convincing, early astronomers could have sworn it was smoke drifting through the stars. But the pipe's eerie resemblance to earthly objects is the least mysterious thing about it. What truly baffles scientists is how these two regions, the bowl and the stem, behave so differently despite being part of the same nebula. The bowl is dense, turbulent, and littered with the chemical signatures of complex organic molecules, while the stem stretches thin, its dust threads pulled into near-perfect alignment by forces we can't yet see. Some researchers speculate this duality comes from a violent past, suggesting the bowl might have been sculpted by shockwaves from nearby supernova, while the stem remains eerily undisturbed. If true, it would mean we're seeing a cosmic fossil, a snapshot of destruction on one end and pristine darkness on the other. Then there's the matter of its neighbors. The pipe drifts close to a cluster of supernova remnants, their ghostly energy still echoing through space. Could these stellar explosions have shaped the nebula's peculiar form? Infrared observations reveal scorched patches along the bowl's edge, where ancient shockwaves might have compressed the dust into its current shape. But the stem shows no such scars, raising the possibility that it formed separately, or that it's shielded by something invisible, like a magnetic barrier deflecting the chaos around it. What makes the Pipe Nebula stand out isn't just its shape, but what it represents, a cosmic crossroads where order and chaos collide. One half whispers of violence, of stars that lived fast, died young, and left their mark on the darkness. The other half remains a silent enigma, its smooth contours resisting explanation. Together, they form a puzzle written in dust and shadow, challenging us to untangle whether we're seeing one story or two, woven together by the unseen hands of the universe. Barnard 163 cuts a curious figure against the star-strewn canvas of space, a cosmic duck frozen in mid-flight, its long, arched neck and rounded body unmistakable once you see it. Unlike the chaotic swirls of most dark nebulae, this one's silhouette is almost whimsical, as if the universe decided to sketch a celestial waterfowl in dust and shadow. But behind that playful shape lies a puzzle that's left astronomers scratching their heads. By all accounts, Barnard 163 should be a stellar nursery bustling with activity. Its density, temperature, and chemical makeup check every box for star formation, yet scans reveal a haunting stillness, no infant stars, no swirling disks of planetary potential. Just silence, as if the entire nebula has been placed on pause. Theories about this cosmic deep freeze vary wildly. One camp argues that Barnard 163 is caught in a rare state of equilibrium, its gravity perfectly balanced by internal turbulence and magnetic pressure, like a cloud held in place by invisible fingers. Others suggest something more exotic. The nebula might be saturated with supercooled molecules, their energy sapped by an unknown process, leaving them too sluggish to collapse into stars. There's even a fringe hypothesis that it's threaded with dark matter filaments, anchoring the gas in place against the pull of gravity. What makes this duck-shaped enigma even stranger is its surroundings. Nestled near the vibrant star-forming regions of IC 1396, Barnard 163 stands out like a glacial island in a tropical sea. While its neighbors burst with stellar newborns, it remains stubbornly dormant, its dust so pristine, it's practically a time capsule from an earlier era. Infrared studies reveal intricate carbon chains and organic molecules woven through its structure, the raw ingredients for life locked in deep freeze. Is this nebula biding its time, waiting for some cosmic trigger to awaken? Or is it a glimpse into a different path, one where darkness lingers and stars refuse to ignite? Barnard 163 doesn't just defy expectations. It offers a humbling reminder that the universe has more than one way to write its story. Sometimes, the most profound mysteries aren't found in the birth of stars, but in the quiet places where nothing seems to happen at all. Floating alone in the constellation Cygnus like a spill of black ink across a starry page, the so-called ink spot nebula stands out for all the wrong reasons. Most dark nebulae blur into the cosmic background, their edges fading into surrounding gas and dust, but this one, it's as if someone took a razor to the fabric of space, cutting out a perfect circle of darkness with unnerving precision. The effect is so stark, early astronomers suspected an instrument error until they realized no telescope, no matter how powerful, could pierce its depths. What makes this nebula truly unsettling isn't just how dark it is, but how abruptly the darkness begins. Neighboring nebulae fade gradually, their dust thinning at the edges like mist. The ink spot doesn't fade, it simply starts a sudden wall of shadow where light goes to die. This sharp boundary hints at something strange happening beneath the surface. Spectrographic analysis reveals almost no trace of the usual molecular clouds found in similar structures, no carbon monoxide, no hydrogen compounds whispering of hidden star formation. It's as if the nebula has been emptied of everything but the finest, most light-absorbing dust particles, filtered down to their most efficient form. Some researchers propose a violent past, perhaps a nearby supernova shockwave blasted away the loose gas, leaving only the densest residue behind. Others wonder if magnetic fields have corralled the dust into this concentrated pocket, squeezing it into unnatural darkness. Then there's the eerie silence around it. Most dark nebulae sit nestled in bustling stellar neighborhoods, their silhouettes framed by distant starlight. The ink spot, by contrast, occupies a celestial no-man's land, with fewer stars in its vicinity than statistics suggest there should be. It's almost as if the surrounding space has been swept clean, or worse, as if stars avoid this patch of sky altogether. Could their absence be coincidence, or is the nebula's gravitational pull subtly diverting passing objects, sculpting its own lonely corner of the cosmos? The greatest enigma, though, is the light it doesn't reflect. Even the blackest nebula usually scatters some starlight, its particles bouncing photons in unexpected directions. Not here. The ink spot absorbs nearly everything, making it one of the darkest natural objects ever measured. In a universe where light is currency, this nebula hoards it, giving nothing back. That level of darkness shouldn't exist without artificial manipulation, yet there it sits, a cosmic void playing by rules we don't yet understand. What lurks in that perfect circle of black? A failed stellar nursery, a graveyard of ancient dust, or something far stranger, a phenomenon we haven't even named yet? The ink spot doesn't just challenge our assumptions about how darkness works, it dares us to reconsider what we think we know about the spaces in between. Lupus 3 is a cosmic shapeshifter, one moment a pool of absolute darkness, the next a glowing veil of starlight. Unlike most dark nebulae that remain steadfast in their shadowy roles, this cloud in the constellation Lupus flickers between identities depending on where you look. Peer at its western edge and you'll find a textbook dark nebula, its dust so thick it snuffs out the stars behind it. But shift your gaze slightly eastward, and the same dust transforms into a shimmering reflection nebula, scattering light from nearby stars like diamonds on black velvet. The transition between these two states isn't gradual, it's startlingly abrupt, as if an invisible line divides light from dark. What causes this duality? The answer lies in the nebula's uneven dance with a cluster of young, hot stars called the Scorpius-Centaurus-OB association. Where these stars' radiation bombards Lupus 3's eastern flank, their energy excites the dust, turning it into a celestial mirror. But the western side remains shielded, cocooned in stubborn darkness. This cosmic tug-of-war creates a laboratory for studying how starlight interacts with interstellar dust, a process that might explain why some nebulae resist illumination while others embrace it. But Lupus 3's secrets run deeper than its split personality. Hidden in its darker recesses, astronomers have discovered something unsettling: rogue planets, worlds untethered to any star, drifting through the void like cosmic orphans. These aren't just any planets, they're Jupiter-sized giants, some glowing faintly with residual heat from their violent births. Normally, such massive worlds would be bound to a star, but Lupus 3's turbulent environment appears to have kicked them loose, sending them careening into interstellar space. The mechanism behind this planetary exile remains hotly debated. Some argue that gravitational tugs from multiple forming stars could have slingshotted these worlds into the abyss. Others suggest the nebula's magnetic fields played a role, channeling chaotic energy in ways that tore young planets from their orbits. Whatever the cause, the implications are staggering. If Lupus 3 is ejecting planets so readily, could our own solar system have lost giants in its infancy? And if these rogue worlds are common, how many might be lurking unseen in the galaxy's dark corners? Perhaps most haunting is what these free-floating planets imply about the nebula's influence. Lupus 3 isn't just a passive nursery, it's an active sculptor capable of both creating worlds and banishing them. Its dual nature mirrors this duality of purpose, a bringer of light and a wielder of darkness, a cradle for stars and a force of cosmic expulsion. In its shifting shadows, we catch glimpses of a universe far more dynamic and far less predictable than we ever imagined. The Dark Doodad sounds like something pulled from a children's sketchbook, a playful nickname given by amateur astronomers to one of the most strangely structured dark nebulae in the sky. Drifting through the constellation Musca like a celestial ruler dropped among the stars, this nebula's defining feature is its razor-straight edge, a geometric anomaly in a universe that usually favors curves and chaos. Most cosmic dust clouds twist and swirl, shaped by turbulence and magnetic fields, but the Dark Doodad, it's as if someone took a knife to the fabric of space and carved a perfect line through it, leaving behind a boundary so sharp it defies everything we know about how nebulae form. What makes this straight edge even more puzzling is what lies along it. When astronomers study the light from stars peeking through the nebula's outskirts, they find something bizarre. The light isn't just dimmed. It's polarized, twisted into a specific orientation, as if the dust particles themselves are aligned with military precision. Normally, interstellar dust tumbles randomly, scattering light in all directions. Here, though, something, whether magnetic fields, hidden shock waves, or an unknown force, has forced these particles into eerie uniformity. The effect is so pronounced, it's like the nebula is wearing cosmic polarized sunglasses, filtering starlight in a way that shouldn't naturally occur at this scale. Then there's the matter of its nickname's irony. The doodad implies something small or insignificant, but this structure stretches over 3 full moons worth of sky, a vast dark spine cutting through Muska's star fields. Amateurs love it for its stark contrast against the Milky Way's glow, a beginner-friendly target that rewards even modest telescopes. Professionals, though, are fixated on its defiance of nebula norms. Why hasn't turbulence disrupted that perfect edge? Why do its polarization patterns suggest a level of organization found almost nowhere else in the galaxy? Some theories point to an ancient supernova shockwave, frozen in time as it plowed through the dust. Others speculate about a hidden black hole's gravitational influence, subtly combing the nebula's particles into order. But no explanation fully accounts for the sheer precision on display. Perhaps the most tantalizing clue lies in what the dark doodad isn't doing. Unlike other dark nebulae, it shows no signs of star formation, no telltale infrared glow of collapsing gas, no protostars flickering to life. It's as if the forces that shaped it also put it into stasis, suspending it in a state of quiet perfection. Whether by accident or design, this nebula stands as a cosmic oddity, a reminder that even in the darkness, the universe has a flair for the dramatic. Straight lines are rare in nature. The dark doodad doesn't just bend the rules, it ignores them entirely, leaving us to wonder what else might be hiding in plain sight, etched into the night. LINS 134 hangs in the constellation Cassiopeia like a broken pane of cosmic glass, its fractured edges glowing faintly against the starry backdrop. Unlike the billowing curves of most dark nebulae, this one looks shattered, an intricate web of cracks dividing its surface into jagged islands of darkness. At first glance, you might mistake it for the aftermath of some violent celestial collision, but the truth is far stranger. These fractures aren't signs of destruction, they're clues to a mystery buried deep within the nebula's icy heart. What makes these cracks so puzzling isn't just their shape, but what they reveal about the nebula's chemistry. When astronomers trained their scopes on LINS 134, they expected to find the usual mix of carbon monoxide and hydrogen molecules that permeate most dark clouds. Instead, the readings defied logic. Carbon monoxide levels were bizarrely low in some regions, as if something had scrubbed the gas clean from entire sections of the nebula. Even stranger, these chemical dead zones aligned perfectly with the cracks, suggesting the fractures aren't superficial, they're windows into a fundamental imbalance in the nebula's composition. One theory points to an unseen culprit, cosmic rays. These high-energy particles streaming through the galaxy at near light speed could be slamming into the nebula's molecules, breaking them apart before they can reform. Normally, interstellar gas recycles itself constantly, with destroyed molecules quickly rebonding. But in LINS 134, something's disrupting that cycle. The cracks might be evidence of cosmic rays carving permanent scars, turning parts of the nebula into chemical wastelands. Then there's the nebula's defiance of radiation pressure. Surrounding stars bombard it with ultraviolet light, a force that typically erodes dark nebulae over time. Yet LINS 134 stands unshaken, its structure resisting the onslaught. Some researchers speculate its dust grains are coated in exotic ices, creating a defensive shell that reflects or absorbs harmful radiation. Others wonder if magnetic fields, twisted into unusual configurations by the nebula's fractured interior, act like cosmic armor. But perhaps the most haunting possibility is that we're witnessing a snapshot of a nebula in transition, one caught between two states of being. The cracks could be stress lines, signs that the cloud is preparing to collapse under its own gravity, or perhaps fragment entirely. If so, LINS 134 isn't just an oddity. It's a living experiment demonstrating how darkness in the universe doesn't just fade, it fractures, resists, and transforms in ways we're only beginning to comprehend. The cracks in this cosmic pane aren't flaws, they're a language spelling out a story of resilience and hidden forces. And like all great mysteries, they leave us with more questions than answers. What happens when a nebula's chemistry breaks down? Can darkness wear armor? And if LINS 134 is resisting the universe's attempts to erase it, what exactly is it protecting? The Black Widow Nebula doesn't just lurk in the constellation Taurus, it sprawls, its spindly filaments stretching across the cosmic web like a predator poised to strike. What sets this dark nebula apart isn't just its arachnid shape, but the invisible force suspected of weaving it, a pulsar that's vanished without a trace. Pulsars, rapidly spinning neutron stars, are typically loud, blasting beams of radiation like cosmic lighthouses. Yet in the heart of this nebula, where astronomers expected to find the culprit, there's only silence. The absence is so glaring, it's as if the universe left behind a fingerprint but erased the hand. Those eerie filaments tell a story of violence. Each twist and knot in the dust suggests an ancient explosion, a supernova so powerful it ejected its collapsed core at unimaginable speeds. The leading theory, the pulsar dubbed the Black Widow for its role in devouring its stellar companion, was catapulted outward, leaving its shredded cocoon of dust behind. But here's the twist: modern surveys can't locate it. Somewhere in the vastness, a rogue pulsar races through the void, its gamma-ray beams no longer pointed at Earth, rendering it invisible to our instruments. The nebula, then, isn't just a remnant, it's a ghostly echo of an escape artist, a cosmic crime scene with no body. Then there's the nebula's most haunting feature, the shadows. When gamma rays from distant quasars pass through the Black Widow's tendrils, they don't just dim, they warp, creating strange, flickering silhouettes on our detectors. It's as if the nebula is a cosmic stained glass window, bending high-energy light in ways dust alone shouldn't. Some researchers speculate this effect comes from the pulsar's lingering magnetic influence, still embedded in the filaments like an afterimage. Others propose the dust itself is laced with exotic particles, remnants of the supernova's nuclear furnace. But perhaps the most unsettling question is what else might be hiding in those shadows. Dark nebulae are already astronomers' blind spots, regions where the universe withholds its secrets. The Black Widow takes that secrecy further, wrapping its mysteries in gamma-ray veils and a missing central engine. It's a reminder that sometimes the cosmos doesn't just obscure the truth, it actively flees from it. And in the silence where a pulsar should be, we're left to wonder, is it truly gone, or are we just not listening in the right language? The Dark Tower rises from the cosmic plains of Scorpius like a monolithic shadow, its pillar-like form stretching over 40 light-years into the void. Unlike the wispy tendrils of most dark nebulae, this structure stands rigid, its edges crisp against the glow of the Milky Way, as if carved by some unseen hand. But what makes this tower truly perplexing isn't just its shape, it's the fact that we can't agree on how old it is. Depending on which dating method you trust, this nebula could be a sprightly 5 million years young or an ancient relic pushing 30 million. That discrepancy isn't just a minor error margin, it's a cosmic contradiction that challenges our understanding of how these structures evolve. Carbon dating molecules within the tower suggest youth, pointing to active chemistry still shaping its dust. But measure the motions of nearby stars, and their trajectories imply the nebula has existed long enough to gravitationally nudge them over eons. It's as if the Dark Tower exists in two timelines at once, defying the laws of stellar aging. Some astronomers speculate it's not a single structure at all, but layers of different aged material stacked like sedimentary rock, each telling a separate chapter of its history. Others wonder if magnetic fields have somehow preserved pockets of its original chemistry, throwing off our measurements like a cosmic sleight of hand. Then there's the matter of its rebellious influence on star formation. Dark nebulae usually birth stars through slow collapse, gravity patiently gathering dust until ignition occurs. But the dark tower isn't playing by those rules. Observations reveal stars flickering to life along its length in a synchronized cascade, as if some invisible wave is triggering their birth. The leading theory, a nearby supernova's shockwave rippling through the tower like a pebble dropped in water, compressing gas pockets into premature stellar nurseries. If confirmed, it would mean this nebula isn't just a passive incubator. It's a cosmic domino turning destruction elsewhere into creation within itself. Infrared eyes reveal the tower's most startling secret: protostars embedded in its sides, not at the base where gravity should pool material. These upside-down nurseries suggest the nebula's magnetic fields are strong enough to counteract gravity's pull in certain regions, pinning stars in place like insects in amber. It's a phenomenon seen nowhere else at this scale, hinting that the dark tower operates under its own peculiar physics. Is it a young structure masquerading as old, or an ancient one wearing a chemical disguise, a passive cloud or an active participant in stellar birth? The dark tower doesn't just stand in space, it stands at the crossroads of our understanding, casting shadows not just on the stars, but on the very frameworks we use to study them. Every unanswered question it poses reminds us that sometimes the universe builds its mysteries not in voids, but in plain sight, tall, imposing, and impossible to ignore. Barnard 343 doesn't just drift through the cosmos, it pulses with hidden structure, its dust and gas arranged in a near-perfect honeycomb of darkness. Viewed through telescopes, this nebula in the constellation Cygnus reveals a stunning geometric pattern, its walls of cold molecular gas partitioning the void into hexagonal cells so precise they seem manufactured. Nature abhors straight lines, yet here they are, etched across light years as if some cosmic architect drafted blueprints for the abyss. But this eerie symmetry isn't even the most puzzling part. What really unsettles astronomers is how these cells move in lockstep, their gas pockets expanding and contracting in eerie unison despite being separated by vast distances. Synchronicity on this scale shouldn't exist without a conductor, some central force orchestrating the rhythm, yet Barnard 343 has no obvious core, no gravitational anchor to coordinate the dance. One theory suggests the nebula might be resonating like a colossal bell, its structure vibrating in harmony after being struck by an ancient shockwave from a long-dead star. Another posits that magnetic fields, twisted into a lattice by some forgotten catastrophe, could be puppeteering the gas from within, but the most tantalizing clue lies in the nebula's appetite for light. Unlike most dark nebulae, which absorb radiation indiscriminately, Barnard 343 devours specific wavelengths with unnerving precision, as if its dust particles were fine-tuned to filter the cosmos. Infrared scans reveal why. The nebula's cells are lined with crystalline ice, a rare form of water frozen into geometric perfection. These icy walls act like cosmic prisms, bending and trapping certain wavelengths while allowing others to pass. The effect is staggeringly selective. Some starlight sails through untouched, while neighboring frequencies vanish without a trace. It's a filtration system so advanced it rivals human-engineered materials, yet it emerged naturally from the chaos of interstellar space. Even stranger, the ice's crystalline structure mirrors the honeycomb pattern itself, suggesting the nebula's shape and its light-absorbing properties are two sides of the same enigmatic coin. Could this be a cosmic incubator for complex chemistry? Laboratory experiments show that similar ice-lined environments can catalyze the formation of prebiotic molecules, the precursors to life. Barnard 343 cells might function like microscopic reaction chambers, their synchronized motions stirring ingredients for organic compounds in perfect rhythm. Or perhaps the nebula is something rarer still, a relic from an earlier epoch of the universe when conditions favored the growth of such crystalline vastness. Whatever the truth, its honeycomb halls stand as a testament to darkness's ability to harbor not just mystery but order, a reminder that even in the deepest voids, the universe has a knack for pattern, precision, and secrets waiting in the grid lines. The Horsehead Nebula needs no introduction. Its iconic silhouette, a rearing stallion carved from cosmic dust, is one of the most photographed wonders of the night sky. But few realize this celestial celebrity isn't alone. Just beyond its flowing mane lies a second shadow, a lesser-known dark nebula whose presence defies simple explanation. Together, they perform an interstellar ballet of light and darkness, casting what astronomers call a double shadow, a phenomenon so peculiar, it challenges our understanding of how these structures interact. What makes this duo so puzzling isn't just their proximity, but the way their shadows behave. The Horsehead's famous profile is backlit by the glowing emission nebula IC434, its edges sharply defined against the radiant gas. Yet its silent partner, a nameless cloud of cold dust drifting nearby, doesn't just dim the light behind it, it warps the Horsehead's own shadow, stretching and splitting it like a ghostly echo. Under certain wavelengths, the effect is unmistakable. Two overlapping silhouettes, one crisp and dramatic, the other faint and distorted, as if the cosmos itself forgot to align its projector. Why doesn't the second nebula simply blend into the Horsehead's shadow? The answer lies in their composition. While the Horsehead is dense and layered, its lesser counterpart is a wispy veil of ultra-fine particles, more like smoke than solid structure. This difference in texture bends starlight in subtly different ways, creating interference patterns rarely seen elsewhere in nature. Some photons skim the surface of both nebulae, while others penetrate deep into one but not the other, resulting in a shadow that's not just doubled, it's fractured, a patchwork of absences. Infrared observations deepen the mystery. The Horsehead glows faintly with the heat of embedded protostars, their energy seeping through the dust. Its shadowy twin, by contrast, remains eerily cold, showing no signs of stellar activity. This temperature gap suggests the two nebulae might not even belong to the same cosmic epoch. The Horsehead could be a relatively young structure, while its partner might be a fading relic drifting into alignment by chance. Then there's the question of magnetism. Recent studies reveal the Horsehead's magnetic fields are unusually orderly, their lines running parallel to its iconic neck. But its shadowy companion, chaos, reigns there, with fields tangled into knots strong enough to trap cosmic rays. This mismatch could explain why the double shadow flickers over time, as erratic magnetic forces twist the lesser nebula's dust into ever-shifting configurations. The Horsehead and its silent partner aren't just neighbors, they're a cosmic experiment in contrast. One is a poster child for the beauty of darkness, the other, a reminder of how much we still don't understand about the voids between the stars. Together, they prove that even the universe's most photographed wonders still hide secrets in their shadows, secrets written not in light, but in the delicate interplay of absence and form. The Ghost Nebula in Cepheus doesn't announce its presence, it lingers at the edge of visibility, a wisp of cosmic gauze so faint, early astronomers often dismissed it as a flaw in their lenses. Unlike the bold silhouettes of dark nebulae like Barnard 68 or the Pipe, this structure seems to hover halfway between existence and oblivion, its edges dissolving into the starfield like smoke caught in a breeze. But what makes the Ghost Nebula truly fascinating isn't its subtlety, it's the way it flickers to life in wavelengths invisible to our eyes, pulsing with the echoes of violence that should have torn it apart long ago. Radio telescopes reveal the truth. This nebula is riddled with scars. Strange, looping filaments within it glow intermittently, their synchrotron radiation betraying the presence of electrons spiraling at near light speed. These aren't just random energy bursts, they're the fingerprints of ancient supernova, explosions so powerful, their shockwaves still ripple through the nebula's dust millions of years later. Imagine a bell struck once, yet still humming with vibrations millennia after the mallets blow. That's the Ghost Nebula, a cosmic resonator, its delicate structure trembling with energy from stars that died before Earth formed. Yet the real mystery is how something so fragile survived at all. Supernova typically shred dark nebulae, scattering their dust across light years, but the Ghost Nebula's wispy tendrils cling together, defying dispersal. One theory suggests magnetic fields act like cosmic stitching, sewing the nebula back together faster than the explosions can tear it apart. Another points to its unusual chemistry, a higher-than-normal concentration of heavier elements that might absorb and redistribute energy in ways ordinary dust can't. Whatever the reason, the result is a celestial paradox, a nebula that should be gone, flickering defiantly in the dark. Then there's the enigma of its intermittent glow. Unlike steady-emission nebulae, the ghost's radio signatures spike and fade unpredictably, as if something hidden within it switches the signals on and off. Some researchers speculate these pulses come from neutron stars, supernova remnants embedded in the dust, their beams sweeping across Earth like lighthouse rays. Others wonder if the nebula itself is the culprit, its tangled magnetic fields creating temporary circuits that amplify radiation before collapsing again. But perhaps the most haunting possibility is that we're witnessing echoes not just of one cataclysm but many. The Ghost Nebula might be a cosmic palimpsest, its layers recording multiple supernova over eons, each explosion leaving its mark in the radio static. If so, this faint smudge in Cepheus isn't just a relic. It's an archive, its whispers carrying stories of stellar deaths we're only beginning to decode. In a universe where darkness often means absence, the Ghost Nebula reminds us that even the faintest shadows can hold the loudest echoes. The Void Nebula in Auriga isn't just another dark cloud, it's a cosmic paradox. While most nebulae wear their shadows like cloaks of dust and gas, this one presents something far stranger, an absence so profound it almost feels intentional. Telescopes trained on its expanse don't just see dimmed starlight, they see nothing, a circular patch of sky where the universe itself seems to have been scrubbed clean. The few stars that do dot its edges don't taper off gradually, they halt abruptly as if meeting an invisible wall. It's not obscuring light, it's erasing it. What makes this void so controversial isn't just its emptiness but scale. Most dark nebulae span a few dozen light years at most. The Void Nebula stretches over 200, dwarfing its peers with a reach that defies conventional explanations. Some astronomers argue its size hints at something unprecedented, not a local dust cloud, but a filament of the cosmic web, the vast, unseen scaffolding thought to connect galaxies across the universe. If true, we're not just looking at a nebula, we're glimpsing the skeleton of existence itself, a thread of primordial darkness left over from the Big Bang. Then there's the lensing mystery, gravitational lensing, where massive objects bend light like a magnifying glass, usually requires the heft of galaxies or black holes. Yet the Void Nebula, despite its apparent emptiness, distorts the light of background stars. The effect is subtle but undeniable, as if an invisible mass lurks within the void, warping space-time without emitting a single photon. Some theories propose a sea of rogue black holes drifting unseen through the darkness. Others suggest exotic dark matter, clumped in ways our models don't predict. The most unsettling possibility, the Void Nebula isn't a structure at all, it's a wound. Simulations show collisions between parallel universes in the multiverse could leave scars like this, patches of space where reality's fabric was stripped bare. Far-fetched, perhaps, but when a darkness this vast refuses to follow the rules, even the wildest theories start to feel like fair game. One thing's certain, this isn't just emptiness. It's a question mark written across the sky, challenging us to admit how much we still don't understand about the spaces between the stars and what might be hiding in plain sight. The Veil Nebula is a celestial masterpiece, a sprawling tapestry of glowing gas, its filaments painting the sky in hues of violet and crimson, all sculpted by a supernova's fury thousands of years ago. But just beyond its radiant embrace, hidden in the same patch of Cygnus, lies something far more enigmatic, its dark twin. Astronomers call it the Veil's dark sister, a nebula so opposite in nature, it's as if the universe decided to carve a shadowy counterpart to one of its brightest wonders. Where the Veil blazes with ionized gas, this structure swallows light whole, its dust lanes weaving a mirror image tapestry of absence. What makes this pairing so baffling isn't just their contrast, it's the timeline. Supernovae are supposed to clear their surroundings, blasting away dust and gas with unimaginable force. Yet here, the Dark Sister's intricate dust lanes persist, threading through the same region as if the explosion never touched them. Some sections even align perfectly with the Veil's glowing tendrils, tracing their curves in negative space. It's like watching smoke and flame freeze in synchronized motion, one frozen in light, the other in shadow. Theories to explain this cosmic contradiction range from the elegant to the extraordinary. One camp argues the Dark Sister isn't a survivor, it's a phoenix. The supernova's shockwave might have compressed nearby interstellar dust into new, denser structures, forging this dark twin from the ashes of the explosion itself. Others propose a sneakier origin. The nebula could be a foreground interloper, a separate cloud drifting between us and the Veil, its dust lanes only appearing to mirror the brighter nebula by chance. But the most tantalizing idea, the Dark Sister might be the Veil's precursor, a cold, dense shell of material that once shrouded the doomed star, its outer layers resisting the blast so stubbornly they linger like a ghost of what was. Infrared observations add another layer of intrigue. While the Veil's gas burns hot, its dark twin harbors pockets of icy molecules, water, ammonia, even complex organics that somehow endured the supernova's inferno. These compounds shouldn't exist here, not after such violence. Their survival suggests pockets of the nebula might have been shielded, perhaps by magnetic fields or sheer luck, creating accidental refrigerators in a furnace of destruction. Then there's the oddity of their interaction. In most supernova remnants, dust and gas mix chaotically, their boundaries blurred by turbulence, but the Veil and its dark sister maintain an eerie separation, their edges sharp as if divided by an invisible barrier. Some researchers speculate this could be evidence of a magnetic wall, a remnant of the dead star's field still rigid enough to partition light from dark years after its demise. The Veil's dark sister doesn't just defy expectations, it rewrites them. In a universe where destruction usually dominates, this nebula stands as proof that darkness can endure, even thrive, in the wake of cosmic cataclysm. It's a reminder that for every blaze of light we admire, there may be a shadow cast in perfect, impossible symmetry. And in that symmetry, we find the universe's quietest rebellion, the refusal to fade. The Maze Nebula in Perseus doesn't just drift through space, it sprawls, its corridors twisting through the void like a cosmic puzzle box left ajar. Most dark nebulae cluster in loose formations, their edges blending into the interstellar medium. But this structure, it's a meticulously divided network, its dust lanes intersecting at near-perfect right angles, creating passages so geometric they seem drawn by celestial architects. Peer through a telescope and you'll swear you're looking at the blueprint for an infinite library, one where the shelves are light years long and the books are written in collapsing stardust. What makes these labyrinthine hallways even stranger is the temperature chaos lurking within. Step from one corridor to the next and the thermometer plunges or skyrockets without warning. Some channels hover just 20 degrees above absolute zero, their dust grains huddling in frigid silence. Others inexplicably simmer at -200, warmed by some unseen energy source, possibly hidden protostars or trapped radiation bouncing between the nebula's unnaturally smooth walls. These gradients defy basic thermodynamics. Heat should smooth out over time, yet the maze preserves its patchwork of hot and cold like a cosmic quilt stitched from opposing seasons. Then there's its eerie silence. Nebulae typically echo with subtle vibrations, sound waves too low for human ears, but detectable as pressure ripples in the gas. The maze, though, absorbs these vibrations like acoustic foam in a recording studio. Stars exploding light years away send shockwaves racing through the galaxy, yet when they reach this nebula, the tremors simply vanish. Some researchers speculate the dust here is uniquely porous, its fractal structure dissipating energy like sand soaking up water. Others point to the nebula's magnetic fields, which crisscross its corridors in braided patterns that could redirect and cancel out vibrations like noise-canceling headphones for the cosmos. But perhaps the most haunting possibility is that the maze isn't just absorbing sound, it's recording it. Theoretical models suggest certain dust arrangements could imprint vibrations into their crystalline structure, preserving acoustic fingerprints of events too ancient for light to remember. If true, this nebula might be a phonograph of the universe's deepest whispers, its walls etched with the echoes of supernova from epochs before Earth formed. We've only just begun tuning our instruments to listen. Between its impossible architecture, thermal contradictions, and soundless depths, the maze doesn't just defy expectations, it rewrites them. Every twist in its corridors poses new questions. Who or what built these passageways? Why do they trap heat so selectively? And what happens to the energy they swallow? One thing's certain, this isn't just another cloud in space. It's a riddle wrapped in dust, daring us to wander deeper into the dark. The phantom streak cuts through Andromeda like a surgeon's scalpel, a dark lane so unnervingly straight and narrow it seems to defy the very nature of cosmic chaos. Stretching 20 light-years across the constellation, this filament of darkness isn't just thin. Its precision incarnate, its edges so sharply defined, they look like they were carved rather than formed by random interstellar forces. Most dark nebulae sprawl or twist, their contours shaped by the push and pull of gravity and stellar winds. But the phantom streak, it's a ruler's edge in a universe that rarely draws straight lines. The math behind its existence is even more baffling. For a structure this slender to maintain its form across such vast distances, it would require conditions so finely tuned they border on absurd. Turbulence alone should have shredded it eons ago. Magnetic fields might explain some alignment, but not to this degree of perfection. Even the most stable cosmic filaments, like those in the cosmic web connecting galaxies, show some variation, some gentle curve or ripple. The phantom streak refuses to bend, as if space itself stiffened along this one narrow path. That impossibility has led to whispers of something far more provocative. Could this be evidence of something artificial? The hypothesis isn't as outlandish as it sounds. Imagine a civilization advanced enough to manipulate interstellar dust, weaving it into a structure for purposes beyond our grasp, a cosmic-scale energy collector, a beacon, or even a boundary marker. While there's no direct proof, the streak's unnatural geometry fits uncomfortably well with certain theoretical megastructure concepts, like a partial Dyson swarm or a light-year-long sensor array. Of course, Occam's razor suggests we're missing a natural explanation, not glimpsing alien engineering. Yet the more astronomers study it, the fewer conventional answers hold up. Infrared observations add another wrinkle. The streak doesn't just block light, it scatters it in bizarrely uniform patterns, as if its dust particles are identically sized and spaced. Natural processes tend to produce a mix of particle shapes and distributions, so this homogeneity is suspicious. Some researchers propose an ultra-rare cosmic event. Perhaps a shock wave from a precisely aligned supernova could have sorted the dust like grains in a sieve. Others point to theoretical phenomena like quantum vortices in interstellar plasma, where exotic physics might impose order at macroscopic scales. But the most haunting detail: the streak isn't static. Over decades of observation, its position has shifted not randomly, but along a fixed trajectory, as if pulled by some invisible anchor. Whatever's guiding this dark thread through Andromeda, it's not just defying nature's tendency toward disorder, it's making a statement, one we're only beginning to decode. Whether the work of unseen physics or something even more extraordinary, the phantom streak lingers in the galaxy's periphery, a slash of shadow where the universe's rules seem rewritten. The Eclipse Nebula doesn't just obscure starlight, it plays with it. Nestled in the constellation Draco, this dark nebula has earned its name not just by blocking the heavens, but by performing a cosmic vanishing act so precise it borders on theatrical. At first glance, it's an unremarkable patch of darkness, but behind it lies something extraordinary, a distant quasar, its brilliant light shining straight through the nebula like a spotlight aimed at a stage curtain. Normally, dark nebulae dim background objects steadily. The eclipse, though, it flickers. Over decades of observation, astronomers have watched as this nebula's opacity waxes and wanes unpredictably, as if something within it is opening and closing celestial shutters. This flickering isn't random noise. It follows a pattern too subtle to be turbulence, yet too structured to dismiss as chance. The leading theory: the Eclipse Nebula might be hiding one of the universe's most elusive objects, a primordial black hole. Unlike the supermassive giants at galactic centers or stellar mass black holes born from collapsed stars, primordial black holes are hypothetical relics from the Big Bang itself, potentially peppering the cosmos like invisible traps. Their gravity could explain the nebula's strange behavior, warping dust into transient lenses that magnify or block the quasar's light in rhythmic cycles. Imagine a black hole no larger than a mountain, yet dense enough to bend the very fabric of the nebula around it, its presence revealed only by the shadows it casts on a quasar billions of light years beyond. Then there's the alignment itself, so perfect, it feels like cosmic coincidence pushed to its limits. Quasars are rare, dark nebulae are common, but the odds of one lining up precisely behind the other, with Earth positioned just right to witness their interplay. Astronomers calculate the chance at less than 1 in a billion. Some argue this alignment isn't accidental at all, that the quasar's light might have guided the nebula's formation, its radiation pressure sculpting dust into a gateway that now flickers like a faulty street lamp. Others propose the quasar's jets, though faint, could be stirring the nebula's magnetic fields, creating ripples that momentarily thin its veil. But the most tantalizing clue lies in the flicker's timing. They don't match any known stellar or interstellar phenomenon. Instead, they echo the theoretical signatures of primordial black holes, objects small enough to evade detection by conventional means, yet massive enough to imprint their presence on the light passing through their domain. If confirmed, the Eclipse Nebula wouldn't just be another dark cloud. It would be a time capsule offering a glimpse into the universe's first seconds, when black holes might have formed from the raw energy of creation itself. What we're witnessing might be more than a quasar's dance with dust. It could be the slow blink of something far older, far stranger, a relic from the dawn of everything winking at us from the dark. The rift slices through the Milky Way in Aquila like a wound in the fabric of our galaxy, a jagged scar of darkness stretching nearly 300 light-years across. Unlike most dark nebulae that appear as isolated smudges against the starry backdrop, this monstrous structure acts as a celestial divider, its tendrils splaying outward like arteries, separating the dense star fields of the Milky Way's spiral arms with surgical precision. But the true enigma of the rift isn't just its size, it's what's happening along its edges. Here, where darkness meets light, something invisible is at work, hurling particles to velocities that defy conventional physics. Telescopes have detected streams of ionized gas racing along the rift's borders at speeds exceeding 500 kilometers per second, faster than most supernova shockwaves. These aren't gentle stellar winds, they're cosmic torrents, as if the nebula itself were generating a magnetic slingshot. The oddest part, there's no visible energy source to explain the acceleration. No nearby supernova, no pulsars, no black holes powerful enough to account for the phenomenon. The particles seem to be surfing on invisible waves, their trajectories curving in patterns that suggest an unseen force is sculpting their path. This has led some researchers to a radical hypothesis. The rift might be tracing a filament of dark matter, one of the universe's elusive threads thought to weave galaxies together. These filaments, predicted by cosmological models but never directly observed, would exert gravitational influence without emitting light, exactly the kind of unseen hand that could explain the nebula's bizarre particle streams. If true, the rift could be our first tangible clue to mapping the dark web of the cosmos, a shadowy highway where ordinary matter rides the gravity of the invisible. Infrared observations add another layer of intrigue. The rift's dust is unusually layered, with temperature gradients that imply it's being compressed from multiple directions simultaneously. Some sections appear folded, as if caught in a tug of war between opposing forces. This isn't the slow, gravity-driven collapse of a typical nebula. It's a dynamic, almost violent process, like watching fabric crumple under unseen hands. Could these folds mark where dark matter's gravitational tides need the gas? Or is the rift a battleground between competing magnetic fields, its dust caught in the crossfire? Then there's the silence at its core. While most dark nebulae hum with the faint radio signatures of molecules like carbon monoxide, the rift's heart is eerily quiet, a void within a void. Yet paradoxically, its outer layers crackle with electrostatic activity, as if the nebula's energy were being pushed outward, leaving its center hollow. This inversion of expectation's active edges, dead core, mirrors the behavior of hypothetical dark matter halos, which are thought to be densest at their peripheries. The rift doesn't just obscure the Milky Way, it interrogates our understanding of the forces shaping it. Every unexplained particle stream, every folded dust lane, whispers the same question: are we staring at a cosmic coincidence or the fingerprint of something vast and unseen? Until we peer deeper into its darkness, one thing's certain: this isn't just a gap in the stars, it's a gateway, and whatever lies beyond is rewriting the rules as we go. The Silent Nebula doesn't just lurk in the constellation Cepheus, it swallows sound. While most dark nebulae hum with faint radio whispers, the molecules within them vibrating just enough to betray their presence, this structure exists in eerie quiet. Astronomers call it the universe's muffler, and for good reason. Point a radio telescope at its heart and you'll hear nothing, not static, not background noise. Just silence, as if someone pressed pause on the cosmos itself. This radio blackout isn't for lack of material. The Silent Nebula is dense, its dust lanes thick with the same carbon-based molecules that typically broadcast their presence across the electromagnetic spectrum. Yet here, they refuse to resonate. The leading theory, something inside the nebula is damping molecular motion at a fundamental level. Imagine throwing a pebble into a pond, only for the ripples to freeze mid-spread. That's the level of violation happening here. Some researchers speculate it's due to an exotic form of quantum friction, where particles interact in ways that cancel out vibrational energy before it can emit detectable waves. Others point to the nebula's bizarre, anti-magnetic fields, regions where magnetic polarity appears reversed, creating pockets that actively suppress rather than align particle movement. The implications are staggering. If magnetic fields can silence a nebula, what else might they be capable of muffling? Could similar mechanisms explain other cosmic radio voids, like the infamous WMAP cold spot? The Silent Nebula's hush might be more than a curiosity. It could be a clue to understanding why certain corners of the universe seem unnaturally quiet. Then there's the nebula's temperature paradox. Despite its radio silence, infrared scans reveal it's not cold enough to justify the lack of emissions. Normally, molecules this still would exist near absolute zero. Yet the Silent Nebula's average temperature sits at a balmy -260 degrees Celsius, warm enough that its particles should be jostling, broadcasting, doing something. Unless, of course, an outside force is restraining them. One controversial study suggests the answer lies in the dust itself. Samples from meteorites show certain nanoscale minerals can absorb vibrational energy when arranged in precise lattices. Could the Silent Nebula's dust grains have formed a natural soundproofing structure, their crystalline geometries tuned to capture specific frequencies? If so, we might be looking at the universe's first known acoustic filter, a celestial baffle sculpted by chance, muting the symphony of the stars. What purpose could such silence serve? On Earth, sound absorption allows for clearer communication by eliminating echoes. Could the nebula's hush be facilitating some form of interstellar signaling we can't yet perceive? Or is this simply nature's way of showing us how much we still don't understand about the interplay between magnetism, vibration, and the void? The Silent Nebula doesn't just hide its secrets, it swallows them whole, leaving us to lean in closer, straining to hear what isn't there. The fossil nebula sits in the constellation Lynx like a cosmic archaeological dig, its dust bands stacked in precise, alternating layers so uniform they could pass for the rings of an ancient tree or the stratified cliffs of the Grand Canyon. But these aren't just visual quirks, they're a timeline. Each dark stripe represents a distinct epoch of galactic history compressed into a single structure. Unlike the chaotic swirls of most dark nebulae, this one is meticulously ordered, its chemistry frozen in time like specimens pinned to a collector's board. Peel back those layers and you'll find isotopes long vanished from the modern universe: hydrogen deuteride, helium-3, and bizarre molecular chains that haven't existed naturally since the Milky Way was a fledgling galaxy. What makes these chemical relics so extraordinary isn't just their age, but their preservation. The fossil nebula's deepest layers are encased in a shell of ultra-dense dust, shielding them from cosmic rays and stellar radiation that would have broken them apart eons ago. It's as if the nebula built its own time capsule, locking away samples of the early universe's raw ingredients. Some of these molecules shouldn't even form under current galactic conditions. They require temperatures and pressures only found in the aftermath of the Big Bang. Their presence here suggests this nebula didn't just witness the galaxy's youth, it's a physical scrapbook of that era's chemistry. Then there's the mystery of its isolation. The fossil nebula floats unusually far from the Milky Way's bustling star-forming regions, untouched by the gravitational tug of war that reshapes most clouds over time. This solitude might explain its pristine state. While other nebulae churn and recycle their material, this one has lingered on the galactic periphery like a hermit, its layers undisturbed for billions of years. Infrared scans reveal just how rare that stillness is. The nebula's core registers at a frigid 8 degrees above absolute zero, colder than even the void between galaxies. At those temperatures, chemical reactions slow to a near standstill, allowing ancient molecules to persist in near-perfect stasis. But the real puzzle isn't how the fossil nebula survived, it's how it formed in the first place. Those perfectly parallel dust bands shouldn't exist without some rhythmic, cyclical process to create them. One theory points to repeated supernova shockwaves, each explosion compressing the nebula's outer layers like a forge hammering metal. Another proposes a long-lost companion star, its orbit dragging tidal forces through the dust like a spoon swirling cream into coffee, leaving behind concentric ripples frozen in time. The most tantalizing possibility, the nebula might be a surviving fragment of the Milky Way's original building blocks, a leftover shred of the primordial gas cloud that birthed the galaxy's first stars. If true, the fossil nebula isn't just a relic, it's a Rosetta Stone for decoding the universe's formative years. Its layers could hold clues to how early galaxies enriched themselves with heavy elements, or why certain molecules thrived in the ancient cosmos only to vanish later. Every isotope locked in its depths whispers a question. Are we seeing a fluke of preservation or a deliberate design, a pocket of the past the universe forgot to erase? Either way, this nebula challenges our assumptions about time's grip on the cosmos. Some darkness doesn't just conceal, it remembers. The Event Horizon Nebula doesn't just blend into the void, it stares back. This perfect circle of darkness in Cygnus earns its name not from its shape alone, but from what happens at its edges. Unlike typical dark nebulae that fade gradually into space, this one terminates with razor sharpness, its boundary so abrupt it mirrors the mathematical precision of a black hole's event horizon. But here's where it gets stranger. While black holes trap everything, including light, this nebula's edges flicker with faint, hawking-like emissions, thermal whispers of energy that defy its otherwise all-consuming darkness. These emissions aren't random noise. Spectral analysis reveals they're tinged with particles resembling theoretical Hawking radiation, the elusive quantum glow predicted to escape black holes. The catch, Hawking radiation requires a singularity's gravitational extremes, yet the Event Horizon Nebula lacks the mass to warp spacetime that severely. So why the mimicry? One camp argues it's a cosmic coincidence. Turbulent magnetic fields near the nebula's edge could be accelerating particles to energies that coincidentally mimic quantum evaporation. Others propose something more radical. What if this nebula isn't hiding a black hole but a natural singularity, a flaw in spacetime's fabric left over from the Big Bang? Such relics, theorized but never observed, could emit similar radiation without the crushing gravity of a collapsed star. The debate intensifies when you examine the nebula's rotation. Its outer dust lanes spiral inward like water circling a drain, moving at velocities that suggest an unseen mass tugging at them. Yet radio telescopes detect no compact object at its core, no pulsar, no black hole, not even a failed star. Unless, of course, the singularity is naked, unshielded by an event horizon, its gravity warping the nebula without the usual shroud of darkness. Naked singularities are among the most contentious ideas in physics, considered mathematically possible but physically improbable. If the Event Horizon Nebula harbors one, it wouldn't just redefine this structure, it'd rewrite our understanding of cosmic censorship, the principle that singularities must always hide behind event horizons. Then there's the eerie silence at its heart. Most dark nebulae hum with the low-frequency vibrations of collapsing gas, but the core of this one is acoustically dead, as if sound itself hits an invisible wall. Gravitational wave detectors have picked up faint tremors from its direction, though ripples that arrive in rhythmic pulses, like echoes from an object falling into an abyss we can't see. Is this nebula nature's way of toying with us, crafting a black hole analog without the black hole? Or is it evidence of something far stranger, a cosmic phenomenon we haven't yet named? The Event Horizon Nebula doesn't just challenge what we know, it forces us to confront what we don't. And in that confrontation, the line between shadow and singularity begins to blur. The Omega Void isn't merely a dark nebula, it's a cosmic titan, a yawning expanse in Centaurus so vast, it defies the very motion of the universe itself. Spanning over 400 light-years, this colossal structure doesn't just obscure starlight, it warps the fabric of spacetime around it, bending the trajectories of entire galaxies drifting nearby. Most dark nebulae are tiny ripples in the galactic pond, but the Omega Void, it's a tidal wave, its gravitational influence so profound, it resists the Hubble flow. the relentless expansion of the universe that should be carrying all matter apart like leaves on a river. What makes this resistance so baffling is the sheer audacity of it. The Hubble flow isn't just a suggestion. It's the universe's baseline, the unstoppable backdrop against which all cosmic motion plays out. Yet here, in this pocket of Centaurus, the Omega Void's gravity grips surrounding galaxies with enough force to countermand that expansion, anchoring them in place like celestial buoys in a rushing current. Some researchers argue its density holds the key. Its core may harbor invisible mass, perhaps dark matter clumped in ways our models can't yet describe, amplifying its pull beyond what visible dust and gas alone could achieve. Others speculate the void isn't empty at all, but a knot in spacetime itself, a relic from the Big Bang's turbulent infancy where the rules of cosmic inflation never fully took hold. Then there's the proto-universe hypothesis, the most controversial explanation of all. A handful of cosmologists suggest the Omega Void's behavior mirrors what we'd expect from a budding universe, a pocket of spacetime with its own nascent laws. In this fringe theory, the void could be a region where inflation stalled, leaving behind a bubble of alternate physics, its gravitational quirks hinting at dimensions or forces beyond our own. While evidence remains scant, the idea is tantalizing. Could this nebula be a window into a sibling cosmos, suspended within our own like an egg within an egg? Infrared surveys reveal another layer of strangeness. The void's edges are too sharp, its density gradient too steep for a structure of its age. Normally, cosmic time erodes such boundaries, smoothing them into the interstellar medium. Yet the Omega Void's walls stand crisp, as if sculpted yesterday. Some propose its interior hosts a low-grade repulsive force, an anti-gravity effect gently pressing outward to maintain its shape against collapse. Others point to ancient shockwaves from colliding galactic filaments, their energy frozen into the dust like a fossilized echo. But perhaps the most humbling thought is this: the Omega Void might not be an anomaly at all. Instead, it could be the first of many, a glimpse into a hidden class of supernebulae whose existence challenges our cosmic senses. If darkness this profound, this defiant, can exist unnoticed until now, what else might loom in the unseen reaches of the sky? The universe has a habit of reserving its deepest secrets for the places we least think to look. And in the Omega Void's silent vastness, we're left to wonder whether we're staring into an ending or a beginning we don't yet have the language to describe. From the ink spot's unnerving precision to the Omega Void's cosmic defiance, these dark nebulae don't just hide stars, they hide truths. Each one whispers a question that leaves our textbooks feeling incomplete. How does the Snake Nebula freeze star formation with magnetism? Why does the Silent Nebula swallow sound like a cosmic mute button? And what force stitches the Event Horizon Nebula's edges with hawking-like radiation without a black hole in sight? These aren't just gaps in our knowledge, they're glaring flashes signaling where the universe might be playing by rules we haven't written yet. Perhaps the most humbling realization is how many answers could rewrite physics itself. The Omega Void's resistance to cosmic expansion hints at gravity behaving in ways Einstein never predicted. The fossil nebula's layered isotopes suggest ancient chemistry we've never replicated. And the phantom streak's unnatural geometry. It dares us to consider whether structure in the cosmos always comes from chaos, or if there's something or someone else at work. But here's the beautiful part: these mysteries belong to everyone. Maybe you think Barnard 68's perfect sphere hides a dark matter scaffold. Or perhaps you suspect the rift's particle jets are tracing the contours of a hidden dimension. That's the thrill of the unknown. It's a conversation without end. So tell us in the comments which nebula keeps you awake at night, and more importantly, what do you think it's hiding? The universe's greatest stories aren't just written in light. Sometimes they're waiting in the dark.